There is a shape sitting in the room with you right now that you are physically incapable of seeing. Not because it's small, not because it's hidden, but because your eyeballs, your brain, your entire evolutionary heritage, simply were not built to perceive it. And the frustrating part? Mathematicians can describe it perfectly. They just can't show it to you. Neither can I. But by the end of this, you'll understand it anyway. So let's get one thing out of the way immediately. When people say the fourth dimension is time, they're not wrong, exactly, but they're also doing the intellectual equivalent of answering what's in this box. With vibes, we're not talking about time. We're talking about a fourth spatial dimension, a real, geometric direction. The kind you could, in principle, walk in, if you weren't a tragically three-dimensional creature with three-dimensional legs. To understand why you can't see it, we need to drop down a level, way down. Let's talk about Flatland. Imagine a creature living on a flat sheet of paper. And I don't mean lying on a piece of paper, I mean inside it. The creature has length and width, but no height whatsoever. It is infinitely thin, which, frankly, is a body type many of us aspire to. This creature can move left, right, forward, and back. The concept of up is not just invisible to it, it's literally unthinkable. Now here's where it gets interesting. Suppose a three-dimensional sphere, a basketball, say, decides to pass straight through Flatland, top to bottom. What is our paper-thin friend experience? At first, nothing. Then, the moment the bottom of the sphere touches the plane, a single dot appears out of nowhere. Then that dot becomes a tiny circle. The circle grows, reaches its maximum size when the sphere's equator passes through, then shrinks back down, becomes a dot again, and pops out of existence entirely. So how would the Flatlander describe a sphere? It would say a sphere is a circle that appears from nothing, grows, shrinks, and vanishes. And it would write a very confident physics paper about it. The Flatlander is not wrong, it's just only ever seeing slices, cross-sections. It can never hold the whole sphere in its mind, because the whole sphere lives in a direction it doesn't have access to. And here's the punchline that should make the hair on your neck stand up. We are the Flatlander. We are the smug little creature on the paper. When a four-dimensional object passes through our 3D world, we only see cross-sections, shapes that appear, morph, and vanish, while the real object sits there perfectly still in a direction we can't point to. We just call it weird and move on with our lives. Okay, so what even is a dimension? Let's strip the mysticism out of it, because the word dimension has been kidnapped by science fiction and forced to mean spooky parallel universe where you have a goatee. It does not mean that. A dimension is just a direction you can move in that's independent of all the others. Start with a line. That's one dimension. You can only go left or right. Add a second, perpendicular direction, forward and back, and now you have a plane. 2 dimensions. Add a third perpendicular direction, up and down, and congratulations, you've got the space you're sitting in. 3 dimensions. So the fourth dimension is just a fourth direction. One that's perpendicular to all 3 of the others at the same time. And right about now your brain is filing a formal complaint, because there's no such direction. You've used them all up. Left, right, forward, back, up, down. There's no leftover way to point. And that's exactly the problem. Your brain is doing the same thing the Flatlander did when asked to point up. The math, however, has no such hang-ups. Mathematicians needed names for the 2 ways you could move along this new axis, so they invented Anna and Kata, the 4D versions of up and down. You will never use these words at a party. But the universe doesn't care about your social life, and neither does geometry. So let's build a 4-dimensional object. And we're going to do it the lazy way, by dragging. Start with a single point, 0 dimensions. It's a dot. It does nothing. Now drag that point sideways, and it sweeps out a line segment. 1 dimension, 2 endpoints. Now take that line segment and drag it perpendicular to itself. It sweeps out a square. 2 dimensions, 4 corners. Now take the square and drag it perpendicular, straight up, and it sweeps out a cube. 3 dimensions, 8 corners. Now do it one more time. Take that cube, and drag it in the 4th perpendicular direction. Anna. What you get is called a tesseract, or a hypercube. 16 corners. And notice the pattern in the corner count as we went. 1, 2, 4, 8, 16. It doubles every single time, because every time we drag, we make a copy of everything and connect the 2. Here's a fun fact to ruin dinner parties with. A cube has 6 square faces. A tesseract has 8 cubic faces. Mathematicians call them cells. That's right. The faces of a 4-dimensional cube are themselves whole cubes. 8 of them, all stitched together through the 4th dimension. If that sentence made you slightly nauseous, good. That's your brain hitting the edge of its hardware. Totally normal. Now, we obviously can't see a tesseract directly, but we can do the next best thing. We can look at its shadow. And shadows, it turns out, are how we cheat dimensions all the time. Think about how a 3D cube casts a 2D shadow on a wall. The shadow is a flat shape, usually a square inside a square, with lines connecting the corners. It's a faithful, if squished, representation of the cube, just dropped down one dimension. We lost the depth, but we kept the structure. We can do the exact same thing with a tesseract. We take this four-dimensional object and project it down into our three-dimensional world, the same way light flattens a cube onto a wall. And the result is the iconic image you've probably seen, a cube, inside another cube, with lines connecting all their corners. And here's the part everyone gets wrong. People look at that and think the inner cube is smaller than the outer cube. It is not. They're the exact same size. The inner cube only looks smaller for the same reason a person standing far away looks smaller, perspective. Except the inner cube isn't further away in any direction you can point to. It's further away in the fourth direction. It's further along the Kata axis. Your brain interprets far away in 4D as small, because that's the only tool it has. Now we get to the part that breaks people's brains in the best possible way: rotation. In 3 dimensions, you rotate around an axis, a line. A spinning top rotates around a vertical line. A wheel rotates around a horizontal one. Always around a line. That feels obvious. It is, in fact, a lie your low-dimensional life has been telling you. The real rule is that rotation happens in a plane. In 3D, when you spin around the vertical axis, you're really rotating in the flat horizontal plane. It just so happens that in 3 dimensions, every plane has exactly one leftover direction perpendicular to it, so we lazily name the rotation after that leftover line. Convenient, misleading. In 4 dimensions, this shortcut collapses, because a plane no longer has just one perpendicular direction left over, it has two. So you have to think in terms of the plane of rotation directly. And here's the kicker: there are 6 independent planes you can rotate in. With our 4 axes, you get the xy, xz, xw, yz, u, and zw planes. 6 ways to spin, instead of 3. Twice the rotational chaos, no extra charge. When you rotate a tesseract in one of the planes that involves that fourth direction, say the xw plane, and you watch its 3D shadow, you get that mesmerizing, hypnotic effect where the cube appears to turn inside out. The inner cube swells up and pushes through to become the outer cube, while the outer cube shrinks down to become the inner one. Nothing is actually growing or stretching. The tesseract is rigid. It's just rotating, rigidly, through a dimension you can't see, and its shadow is doing its level best to keep up. Let's go back to spheres, because we owe Flatland a sequel. What does a 4-dimensional sphere, a hypersphere, look like as it passes through our world? Run the exact same logic, one level up. First nothing, then a single point appears out of thin air. Then a sphere, a full, solid, 3-dimensional sphere that grows, reaches a maximum, shrinks back down to a point, and vanishes. A sphere that appears from nothing, grows, shrinks, and disappears. Where have we heard that before? We are now the confused Flatlander, writing our confident little paper about the magic disappearing sphere. So is this all just a beautiful party trick? No. The fourth dimension shows up constantly in real math and physics, just usually wearing a disguise. There's spacetime, where time is treated as a fourth coordinate, though, as we promised, time genuinely isn't a spatial dimension, it just plays one in Einstein's equations. There are quaternions, a 4-dimensional number system that every video game on Earth uses to rotate 3D objects smoothly without glitching out. There's string theory, which casually asks for 10 or more dimensions and then hides the extra ones by curling them up impossibly small, because of course it does. And then there's the most practical one of all. In data science, every variable is a dimension. A spreadsheet with 100 columns is, mathematically, a 100-dimensional space, and data scientists swim around in it all day without blinking. The fourth dimension isn't exotic to them. It's a Tuesday. It's the warm-up. So here's where we land. You can't see the fourth dimension. You can't point in that direction. Your brain will never render it, no matter how hard you squint. But you can describe it with perfect precision. You can compute with it. You can build cubes in it and spin them and project their shadows down into our humble 3-dimensional world. And those shadows are some of the most beautiful objects in all of mathematics. We are the Flatlander, and these are our glimpses of something larger. If this stretched your brain into a fourth dimension it didn't know it had, subscribe to Improper Integral for more visual math and science. We'll keep casting shadows. You keep watching them.